Hello everyone, I am Abdirizak Ali and I'm affiliated with the Ali Naimi Petroleum Engineering Research Center, and today I'll give you a brief overview of the X-ray CT scanner. This is the outline of my presentation today. I'll first go over the working principle of the X-ray CT, followed by some applications in the petroleum industry, and close with some miscellaneous information on the device. Starting off with how it works, the simplest way to explain a CT scanner would be to compare it to a three-dimensional X-ray machine. There's an X-ray emitter which produces X-rays which go through the sample, and behind the sample are detectors to measure how much of the emitted X-rays are left after going through the sample. While a conventional X-ray machine produces a 2D image from a single perspective, the emitter and detector on a CT scanner revolve around the sample while taking multiple images from different perspectives and reconstructing them to give a 3D visualization of the subject or the sample. Sorry, these were the 2D images from the X-ray and the 3D image that is given by the CT scanner. Now that we have a general idea of what the X-ray CT is, we ask ourselves, how are the X-rays emitted? Well, most X-ray CTs produce X-rays in an X-ray tube, whose schematic you can see here. There is a cathode and an anode, which have I'm sorry for the interruption. I think my pizza.
I think the pizza has arrived. Go for it, Ali. Okay. Grab the pizza. Okay. This is the time when somebody is supposed to share a joke. I have to say.
Who's there?
Excuse me?
The knock-knock joke is good now.
Yes, knock-knock. Who is there?
Pizza.
Pizza who? Okay, I don't know how to follow.
Not Tamimi pizza.
Yes.
Thank you for the very pizza.
I'm back, Professor.
Yes, Ali. So
sorry for
looking forward to continue. Go for it.
Okay, so I was saying that most X-ray CTs produce X-rays in an X-ray tube, and the schematic is on the slide. There is a cathode and an anode which have a very large potential difference, and the cathode consists of a filament which gets heated up as current passes through it, and through thermionic emission, electrons are released from the filament and get accelerated towards the target on the positively charged anode due to the large potential difference. The bombardment of the target by the electrons results in conversion of energy to heat and X-ray photons. Heat makes up about 99% of this converted energy, and therefore the anode needs to be cooled, while the remaining 1% is the emitted X-rays, which are then beamed towards the target that the CT is scanning. You might wonder how or why there is an energy conversion as the electrons bombard the metal target, which is usually tungsten. Well, if we consider it at the atomic scale, there are two possible mechanisms for this. First, when a speeding electron collides with a tungsten atom, it knocks loose an electron in one of the atom's lower orbitals, and an electron in a higher orbital immediately falls to the lower energy level and releases its extra energy in the form of a photon. And this is a big energy drop, so the released photon has high energy, and this is basically the X-ray photon that is produced. Another thing is that free electrons can also generate photons without hitting an atom. An atom's nucleus may attract a speeding electron just enough to change its course, and the electron slows down and changes direction as it speeds past the atom. And this slowing down action causes the electron to emit excess energy in the form of an X-ray photon. Now that we know the physics behind how an X-ray CT scanner works, we must ask, what do we measure and how do we interpret it? Well, we basically measure the attenuation of the emitted X-ray beam. We know the amount of photons emitted at the source, and we detect a smaller amount of photons at the detectors after the beam goes through a body. And this attenuation is proportional to the properties of the body through which the beam passed. Using this attenuation information and travel time knowledge, we can reconstruct an image of the body through which the X-ray beams passed. And this is an inverse problem, as Professor Carlos previously mentioned in the class. Moving on to some applications of the X-ray CT in the petroleum industry. However, first I would like to debug a common misconception that a lot of people have, because this will be relevant to some of the applications I will discuss. It's quite easy to imagine an oil reservoir as sort of a subsurface lake, which we just drill into and produce oil out of, sort of how you would suck juice from a juice box with a straw. This is, however, false. And in reality, an oil reservoir is more like a sponge with lots of small pores in which the oil sits. And now that we know this, how can a CT scanner be useful to us? Well, characterizing the reservoir rock and understanding its properties is extremely important for us to design an optimum recovery scheme. And using a CT, we can actually visualize the pore network in a rock sample. And by this, we can calculate the porosity, and from this indirectly the permeability as well. These are very important parameters and will practically determine how you will produce your oil. We can also use CT for visualization of dynamic processes and flow experiments. For example, here we see images from a CT visualizing the dissolution of carbon dioxide in the pores over time. And this brings me to the last part of my presentation. Some of the most popular manufacturers of CT imaging equipment include GE, Tescan, Siemens, Philips, and Toshiba. And the approximate unit cost depends on the number of slices. This is basically the clarity of your CT. For instance, with a 16 slice CT, it means 16 cross-section slices are used to reconstruct the 3D image. And the more the slices, the better the clarity you have in your images. And of course, the more you'll pay for your machine. And this value can be up to more than $2 million for 256 plus slices. At the Ali and Naimi Petroleum Engineering Research Center at KAUST, we have a powerful multi-resolution X-ray micro CT, which has been optimized for geoscience applications. It can measure as small as 3 micrometers, and its temporal resolution is less than 10 seconds. What this means is it does a complete revolution of the sample and collects data for a full 3D image in less than 10 seconds. The Anperk micro CT can characterize samples from micrometer dimension up to 1 meter in length, and also up to 45 kilogram samples. And with this, I have reached the end of my presentation today. Thank you very much for your attention.